Welcome everyone, and thank you very much for joining us. So I think we'll get started with today's session, and I think we've got a few more people joining us as we start. So that's really good. So first of all, thank you very much for joining us, and welcome to today's session on the future of robotics and intelligent systems. And this is put together by the Department of Engineering at the University of Cambridge, and this is following on from an international workshop we had in Embodied Intelligence. And we're trying to really introduce some of the new kind of concepts of intelligence and robotics to the wider community, and hopefully inspire the next generation of roboticists and computer scientists. So I'm Josie Hughes, and I'm going to be joined by a number of other leading experts in robotics from a number of different universities later on in today's talk. So just a brief summary of what we're going to cover today. So we're going to start with a talk on the future of robotics and intelligence. So where are we today, and what's the state of the art? We're going to try to tie in both kind of first principles, introduction to machine learning and computer vision, but also show some examples of this theory in state-of-the-art robotics research. I'm going to have a panel discussion in about 40 minutes, bringing in some of the experts we have and really trying to get your questions. So thank you for those of you that have already submitted those, and please do keep those coming in. And then finally, we're going to end up with a short activity to do at home in the classroom, focusing on embodied intelligence and this idea that we're going to introduce throughout the talk. So hopefully it will be engaging and informative, and also tie in some of the concepts perhaps you're learning at school or have heard them before to something a little bit new. So just before we start, I'm just going to talk a little bit about my background and what I'm interested in. So I'm a roboticist. I did A-levels in maths, physics and chemistry, and I went to university and I studied general engineering, after which I did a PhD in robotics. And I am now doing a postdoc and starting my own lab shortly. And I'm really interested in how we can achieve complex robotic systems. So how can we create robots which show capabilities equal or equivalent to those of humans? And specifically, how do we design and fabricate these complex robots? So what does this mean I actually do on a day-to-day basis? So I look at how we can fabricate new robots. How can we create design methods, control approaches, and also look at a number of different applications. And this is all words, but what does this mean kind of on a day-to-day basis? So to give you an idea of kind of what my work looks like, here is a slide of kind of my lockdown. So my lockdown, and you have to excuse the mess here, was a lot of playing around with robots, some electronics, 3D printing, kind of fabricating systems and testing them. So it's really about how do we build and understand robots, and how do we create new materials and new kinds of intelligence within robots. So on to the talk of today, and we're going to start with talking about kind of current state-of-the-art robotics. Where are we in terms of intelligence, machine learning, and kind of how can we apply some of these state-of-the-art techniques to robotics? So I wanted to start by highlighting some of the huge advances we've seen in robotics in the past few years and where we are now. So starting here with industrial robots. We've got huge capabilities for robots to perform very precise and repeated movements. So for example, here we see robots building cars in very automated ways. So these robots are really fast, they're precise, they're making use of pneumatics and these robot arms, which 6 degrees of freedom, are very precise in their positioning. And robots are really good for these kind of applications where we have a known environment and a very fixed task. We can also see some of these fantastic videos from Boston Dynamics. I'm sure many of you will have seen these. So this is really incredible. So we've got these robots performing jumping, kind of standing up, star jumps. And this is really incredible. And this is both very impressive physical kind of complexities, but also the intelligence side. So the control and the learning to be able to do this. So that's one side. Another example we had is here of shadow hand. So these are some incredible robot hands, and they're designed and inspired by our human hands. So we've got the many joints, the many muscles, and this allows robots to start performing tasks that we can do as humans. So here, opening a box. We're also starting to see kind of tactile perceptions, so skin-like sensors offered to these hands. And finally, a more industrial kind of focused one is here, with the accompanying music from Da Vinci, is the Da Vinci medical robot. So this is an autonomous robot that medical kind of doctors could use to autonomously and robotically assist with surgery. So here we see a robot being used to sew or suture a grape. So we're really seeing the precision at which robots can be used and how they can be applied to these really challenging tasks and applications. So these are all fantastic demonstrations of where we are with robots now and really impressive. But what's at the heart of these? What is a robot and how can we understand it? So I'm going to start first with what we can call the traditional approach to robots. And all robots can be thought of as having three components. We have a sense, think, and act component. So we have a brain that does some kind of thinking. And then once we've decided what the brain wants us to do, we can act and we can have some kind of interaction with the environment. So this could be moving around, this could be doing some manipulation. Finally, we have some sensing. This could be visual, it could be touch. So we learn something from our interaction with the environment, we update our brain, and we can update how we think about the world. Now, this gives us a very simple paradigm for describing how kind of robots works and interacts with the environment. And we can take this at a very simple level. So let's say we have a very simple robot. So this is just an NXT robot that I'm sure some of you may have even used or seen before. And on this, we've got a very simple sensor, which is an ultrasound sensor, so it tells us the distance from the wall. So we can use this sense, think, act paradigm to sense the environment. Let's say with our ultrasound sensor, we say, is the wall close to me? We make decisions. So we say, oh, I think, we're close to the wall, we should move away. And we can act. In this case, the robot can use the motors and the wheels to move away. So you can see how this sense, think, act paradigm can be used to frame the kind of intelligence and kind of computational kind of decisions of robots and how they also interact and sense the environment. But this paradigm is quite powerful because it can be expanded to many other concepts and very complex situations. So on the left here, we have a self-driving car. So we can use this sense, think, act paradigm again. So for example, this car wants to overtake the other. So we can do some sensing. We can say, where is the other car? And what parameters do we have in the environment? What do we need to avoid? We can then think, we can plan our route. So how can I overtake this car? I need to turn left and go around the car. And finally, we can perform this action. So this iterative continuous loop can be applied to many real world scenarios. And the other one here on the right, we have is robot football playing. So again, we can use the sense, think, act framework. So for example, we can have the robots here, our little mini football players can sense and see the world. They can perform some thinking, they can coordinate together, they can select what action or motion they want to perform, they can act, they can move, they could kick the football, and we again update and go around this cycle. So this is one way we can think of robotics. And on this, we have a number of key components. Now, obviously, to act in the world, we have mechatronics and actuation. So we perform some action on the world. On the sensing side, we have predominantly kind of computer vision. We also have tactile sensors. We could have many other types of sensors. We could have temperature sensors. We could have kind of other touch sensors. And finally, we have thinking. Now, this could be very simple, just from a kind of a decision statement, like as we had with the Lego robot. It could just be an if statement that, you could write in a very simple Python script. But we can also start using machine learning and deep learning to actually augment and perform this thinking and this decision making. Now, things do start to get a little bit muddled here because, for example, computer vision is coupled very much with machine learning and deep learning. So this control and this thinking and this sensing kind of aspect is very much coupled, as we'll hopefully see going forwards. So we've tapped on these topics very much here of machine learning, deep learning. And these topics are very much used and bandied around in the media and et cetera, et cetera. But what do they actually mean and how can we use these in a robot to build intelligent controllers and smart brains? So let's first of all start with the definitions. So I don't know about you, but I think it's always a bit confusing what we mean by these terms. And one way we can think of them is being kind of structured. So at the highest level, we have artificial intelligence. And this is kind of trying to develop techniques that allow computers to mimic or show human-like intelligence. So this is obviously very broad and something that we really want to achieve in robots. Below this, we have a kind of subsets. We have machine learning, which is one subset of this. And this is techniques that enable machines to improve at tasks with experience. So then you might need some supervision, they might need some data, and some input perhaps from a human to design the framework for doing that. Now, a subset of machine learning is then what we're calling deep learning. And this allows a machine to perhaps even train itself to perform a task. So we've got this hierarchy. And it's worth saying artificial intelligence is not a new topic. It's been studied and investigated since the kind of middle of the 1900s or kind of earlier, and likewise with machine learning and deep learning. So some of these are quite old-fashioned techniques and approaches, but we're now just getting the computational capabilities which actually allow us to utilize some of these approaches, which is why at the moment we're really seeing this explosion in applications of machine learning and deep learning, which is the newest of these techniques. But what is machine learning versus deep learning? I think this is quite a confusing area. So machine learning is essentially, we want to have an input and we want to produce an output or predict that output. Now, when we talk about traditional machine learning, there's some element of pre-processing to extract what we call features which describe that input data. So we do some pre-processing on the data and we then perform some kind of task. It could be classification, it could be prediction to get our output. Now, on the other hand, deep learning, we take the input and from that we directly represent the output. So we remove this initial layer of feature extraction. Now, on one hand, this is really great because it learns itself how to perform a task and it really is scalable with more data. However, on the other side, it can be very beneficial to have some feature extraction in there. For example, as a human, let's say if we want to learn, for example, can we identify images with cats and dogs? We know there's certain features that help with that. So being able to actually help and assist with that initial feature extraction process can be very beneficial. But this is a very high level is where machine learning and deep learning vary. Now, there are many variants and techniques for doing machine learning and deep learning, but looking at machine learning, we can, especially in the context of robotics, we can broadly describe these as three different areas. So within machine learning, we have supervised machine learning, we have unsupervised learning, and we also have reinforcement learning. Now, lots of different types, lots of different terminologies, but what do these really mean and how do we perform these? So when we're talking about unsupervised learning, this is when we give machine learning some training data. And this is labeled training data. So let's go back to our cats and dogs analogy. If we want to develop some machine learning algorithm that could predict these, with supervised learning, we'd give it lots of training samples and images of our cats and dogs. And these would be labeled saying, this is a cat, this is a dog. And we could then train our machine learning algorithm to then classify unseen pictures of cats and dogs. So supervised methods are very good for predicting next values and actually assigning a label to this. Now, unsupervised machine learning is quite different. Here, we use unlabeled training data. So let's go back to our cats and dogs analogy. Here, rather than providing labels on our cats and dogs, we just put lots of cats and dog images. And we would say, perhaps, we know there are two clusters. We would then use the machine learning algorithm to automatically identify these clusters without these labels. Now, this is really great because we don't have to label them, but equally the output we get is slightly different. So there's trade-offs here between supervised and unsupervised data, as we'll see in a second. And the final, perhaps most useful approach for robotics is reinforcement learning. And this is where we can learn from our mistakes. So we use feedback, so we, in a very human kind of bio-inspired way, we interact with the environment and use perhaps negative response. So let's say we're trying to pick up a cup, or let's go back to cats and dogs. We're trying to classify cats and dogs. In reinforcement learning, if we make a mistake, we could learn from our mistake to understand our learning and perception and improve from that. So this is a very kind of feedback-driven means of learning. So how could we implement a very simple supervised learning approach using machine learning? So at a very broad level, to perform supervised learning, we want some input data. And we put this into some kind of model, which we'll come to in a moment, and we perform some kind of training on that. So we take our data set, which is labeled, and we assign, how can we train a network to assign the input to the output? And using that trained model, we can then test our model by having new input data and seeing if it can predict correctly the output. Now, the interesting thing is, what is this algorithm in the middle? How can we actually build up this model that can be used to do this machine learning and prediction? And what we're hopefully going to show you is it can be very, very simple. So the simplest way we can perform some machine learning is through regression. Now, this is something I'm sure you've all done in maths. So it's at a very simple level, can we actually just fit a linear expression, so a y equals mx plus c, to our data? So for this example here on the left, let's say we're trying to predict the weight from the height. Let me try and get it into this bar. So our input to our trained network is height and weight. So we have lots of height and weight from people. And our network, we want to perform some regression to then allow us to predict in the future the weight from the height of an animal. So from our training data, we can fit a linear model. So our y equals mx plus c into this. We get our values from this, and then to test the model, we can, for any particular value of height, use our y equals mxc to predict our value of y. And that is an example of machine learning using regression. Now, obviously, this is a very simple linear fit. We can expand this, for example, to have a polynomial fit or another function. So this is incredibly simple, but provides a means of performing machine learning. Now, that's very computationally easy to do. I think a lot of you could sit down now and write that script in Python or use Excel. But obviously, that's a very simple task. As we get more complex and the tasks require more nuanced approaches, we can use a lot of other different approaches. So one here is called a support vector machine. And here, let's say we want to perform some kind of classification. So let's go back to, we have our cats and dogs and we want to separate these. And we have features that we've extracted. So let's say we've extracted two features. So one could be size of the ears and the other could be, I don't know, length of the tail. So these are our X1 and our X2. And we can plot these features that we've measured of our cats and dogs. What we can then do is we create these support vectors, and these aim to be kind of our two-dimensional vectors which separate these two groups by what we call a hyperplane. And by defining this hyperplane, we define the point which best separates these two groups with our support vectors as far away from each other as possible. And this allows us to define the two areas and therefore classify our cats and our dogs using our features in this way. Now, obviously, here in this case of the green and the blue dots, they're nicely separated, but this is not always the case. So what we can often use before this is actually we can transform our space in our feature space to another feature space which better separates these. And this allows us to create and identify these hyperplanes that best separate our values in this kind of supervised manner. So this is showing how we can perform supervised machine learning, and we can take very simple ideas and build these up to create very complex machine learning classifiers and predictions. But this is great, but we have to get a lot of labeled data, and as I'm going to show you later, getting labeled data is time consuming and expensive. So we don't always want to have to go through this when we're performing some kind of task to do some kind of identification or perform some kind of task. So another approach, as we've discussed, is unsupervised machine learning. So an example with this is we have lots of input data. So we could have pictures of, let's say, apples and watermelons. We want to create our machine learning model, which can then separate these two into two groups, so classify them. But we don't tell the model what is the difference between it. So we're expecting the model to do some kind of automatic classification and separation of these two different groups on some kind of features. And this is extremely powerful and used for example, identifying key features that identify different data. So kind of what we might call principal component analysis. So if we have very complex, high dimensional data sets, reducing it down to just the key dimensions which best describe these different data sets. And one very popular way of doing this is what we call Kmeans. So in our unsupervised data, we have, again, let's say our cats and dogs, let's say we have 3 animals now, and we have, again, our features. So let's say their tail length and their ear height. And we have our data in our 2D plot here. So at the moment, we have no labels. We do not know how we can cluster or classify these. What we'll start by is saying, we know we have 3 groups. So we're going to assign kind of the mean location for these groups, so our 3 means. And we create clusters around these means. And what we do is we partition the space that around these means, and we cluster them based on these points. And the center of these clusters, centroid, it allows us then to classify these different groups. And what we do is we repeatedly assess new centroids that best separate our different objects in our feature space that give us the optimal and tightest clustering. And we repeatedly iterate, moving our centroid around with the 3 to optimize for minimizing the error between our centroid and our different points in our feature space. And in this way, we can automatically classify and identify the groups of points in our feature space that best rectify our groups. So with no labels, then we get this estimation of the different groups. So an example of this that's very commonly used is, for example, how do we identify different species of plants? So for example, if we had all these different points in our cluster space, we can use Kmeans to automatically identify the different species just by performing this iterative Kmeans algorithm. And again, this is very powerful because it's a relatively simple technique, but we can apply it to very complex problems and use it to perform very real-world problem-solving tasks. And another place we use this kind of machine learning approach is very widely is in computer vision. Because as you see, these are tasks that very nicely tie into this framework. And if we look at computer vision, there are many different types of problems. We have to be very careful when we're talking about computer vision, what we actually mean. And there are many what we call traditional approaches to computer vision, which are kind of more mathematical in framework, rather than using some of these probabilistic machine learning techniques. But what do we mean by computer vision, and how can we use machine learning to help us? Now, the easiest thing we've already talked about is classification. So we've got our cat and dog. Our first problem, as we see here, is classifying. It's saying what is in the image. Is this a cat or is it a dog? But the second problem we come across is localization. So we actually want to say in this image, not just what is it, but where is it? So here, for a symbol object, we can actually put up what we call a bounding box around it and identify it as a cat. The next stage is also object detection. So here we could have multiple instances or objects in an image, and we can identify what they are and where they are. And then the final one is what we call semantic segmentation. So in our image, what actual pixels or parts of the image belong to that object? So for example, what pixels are a cat and what pixels are a bowl? So you can see here we have many different tasks. Now, some of these are best suited for supervised learning. For example, classification and localization. As we've talked about, if we want to be able to identify a cat and dog, we need to have lots of labeled data of cats and dogs to throw at it. We could train, for example, our SVM-based classifier, and then we could test that on unseen images. However, another approach for the semantic segmentation is we could use our clustering. For example, we see that our cats have this very grey colour in comparison to everything else. So if we viewed this image rather in pixel space, but in terms of colour, so we could have our RGB coordinates, could be our feature space, we could use, for example, our unsupervised Kmeans clustering to cluster together different areas of the same pixel colour. And that could allow us to perform this semantic segmentation where we extract which pixels correspond to which object. So here you can see how we can use different types of machine learning, for example, in computer vision, and where and why you would want to use both unsupervised and supervised learning in different ways. Now, the final type, which is perhaps most relevant to machine learning, is reinforcement learning. And this is where we actually learn to perform a task through repeated interaction with a dynamic environment. And we use the feedback signal or the reward from this to augment our future action. And this is very much kind of trial and error based. So it allows the robot to learn through trial and error how best to interact with the environment, and it updates our future performance. And it's famously the example that was used for AlphaGo. So to perform this, we have some kind of control or policy, and that decides what action we want to perform on the world. So we're going to take a very simple example of learning to grasp, and we're going to be grasping a pen. And first of all, how do we pick up that pen? So let's say our reinforcement learning policy says we want to pick it up X% of the way from the end. And we might try with a value of 30% first. We'd perform the action, we'd see how well it performs, and we'd get a reward. And this could be success or failure. And using this both observation, so let's say if we pick it at 30% at the end, it's not stable, so we can't grasp it and it fails, would then form and update our policy. And it would tell us, okay, picking up 30% at the end didn't work, so let's update and let's try 50%. We could then try 50%, and with this updated action, we could then find that actually we can pick up this pen successfully. So through this iterative trial and error approach, we can build up and allow the robot to learn how to perform many complex tasks. And this is really exciting to the world of robotics, but there is a downside, as hopefully we'll summarize shortly, in that it requires lots and lots of data. So Google have set up this very exciting platform, which they have lots of robot arms in a room. And I think they left them for a period of weeks, continuously doing what we talked about, trying to grasp these objects and learning how to pick up. So these pick and place, so where if you have your fork or your bottle, how do you pick up these objects? And learning, if I fail, how can I try again? So it's combining computer vision with this robot to learn ways of picking up these objects. But you can see here, even to perform these pick and place tasks, which we would perform with ease, for the robots, we've got to perform many, many hundreds of hours of experiments to even begin to learn how to do this. So although it's still a very impressive and exciting contribution to robotics, we've still got this problem with how can we expedite experiments such that we don't have to have Google kind of power computational resources and many robot arms picking for hours and hours in a room. So one approach to doing this, of course, is deep learning. Now, this is something, again, which is a term that's used very widely, and it's kind of somewhat misunderstood as to what it actually means. So we're going to start right at the beginning with a simple neuron. So neural networks are inspired by our brains, and indeed at the heart of our brains are neurons. So these essentially, we have sensory neurons, we have an output neurons, so they really form the basis of our brains. And in these, we have, as we see on the left, we have these kind of dendrites. They collect signals from around our bodies, they perform some kind of function, and they output it at a synapse. And they're very simple structures that we can represent artificially, as you see here on the right, as having some kind of inputs, which, for example, could come from our dendrites or elsewhere in our body. They then perform some kind of summing function, where for each input you multiply it by the weight, and then you perform it to the output. So it's essentially just a sum, a weighted summing function. And this is what we can call our neuron. And this essentially would be a very simple single layer neural network. And all it does is it outputs the weighted sum of our inputs. Now, how can we do anything with this? This is just a very simple kind of calculator. Now, the first thing we can do is turn it into what we call a perceptron. Now we have we had our artificial neuron, but what we do here is we just put another function at the end. So we take the output for our weighted sum and we put it into a function. Now, the simplest function we can have here is a step function. And this is just essentially a function which we say if our output from the weighted sum is above one value, it's high, or if it's below this other value, it's low. So it just gives us a binary output from a continuous input, and we can manually set the output of the step function. And this allows us to do very simple classification. So again, we're going back to our cats and dogs, apologies again, but we can actually use this perceptron to perform some kind of classification. And if we change the weights and the weighted sum and the kind of properties of our step function, we can actually change the classification task that we perform. So very simply, we can take these very simple single kind of neuron structures and actually start building up some kind of complexity and some intelligence. Now, this is just a simple neuron, but we have neural networks. So how do we take this and build up a whole level? So what we do is we have three components to our neural networks. We create many hundreds of thousands of these single kind of artificial neurons, and we put these into layers. We have our input layer, which would be the input data, so our training data or our test data. We have our hidden layers, and these are the bits that perform some kind of function. So they do our kind of summation, and then we kind of have different layers combining this together, and we finally get our outputs. And these are good because these represent lots of complex computations, these weighted sums from our input to our output layer. But to get it to actually perform a task that we need to do, we need to train and identify the optimal weights and functions. So this is what we call training when we're performing our network. And this has two kind of really key stages. So the first one is we have our network, we have our inputs, our hidden layer, and our output layer. And we have all these weights associated to each of these functions. And the first thing we do is forward propagation. So we make an estimated guess at what each of these weights should be. And from that, for all our different training data, our inputs, we then calculate the output. Now, this is not going to be accurate. We're going to have some error. So what we next do is back propagation. We want to then update our weights to minimize the error between the actual answer and the guessed answer. So for each of our input training data, we calculate the error, which we call as a loss function, and then we want to optimize our weights to minimize that loss function. And what we can do is we can iterate this cycle. So we can update the weights, we then test again with our forward propagation, we then optimize again with our back propagation. And over time, the network will become increasingly accurate, so it will minimize our error. And this way we can train our neural network, and then we can start using it to perform a number of predictive tasks. So here you can see we can build from a bio-inspired single neuron up to a whole neural network, and we can get very intelligent behaviors. So how do we actually apply some of these techniques to robotics? One problem we're quite interested in, and you'll hear a bit later, is about agriculture and agricultural robotics. So how do we create robots that can adapt to variable conditions? So we're looking here at how can we create robots that can harvest iceberg lettuce? Now, this is the first challenge you see. We have a sea of green and we want to harvest and iceberg lettuce. But to do this, we first need to localize and identify where the heads of lettuce are. So we want some kind of machine learning system that can output the location of our lettuce. And to do this, we get a lot of training data and we perform supervised machine learning. So we gathered over 1,000 images of lettuce and we train a neural network to predict where the lettuce are from the data. And although this is a very effective means, it means someone manually had to go around and manually label where the lettuce were on each of these 1,500 images. So this kind of really demonstrates some of the downsides of machine learning and why unsupervised techniques can be quite advantageous. So we used a two-stage classifier here, one to do localization and one to use classification. And we can use some of those techniques and we can actually test this in the field. And by having localization data sets, which are not just from one field of lettuce at one day, but in different weather conditions, we can create machine learning approaches which are quite robust. And we've implemented this actually on a robot in conjunction with an iceberg lettuce harvester. Now, a second interesting question is how can we learn and use some of these machine learning techniques in robot cooking? And we're particularly interested in how we can learn to cook an omelette. So one of the students in the lab over the summer built this robot that actually makes an omelette. So it starts from cracking an eggs, adds pepper and salt. It performs some mixing of the egg mixture, and it actually pours this into a pan and performs the cooking process. Now, this is great, but different people like their omelettes in different ways. So how can we optimize the amount of pepper, the amount of salt added, the amount of cooking time to meet people's expectations? So what we can do is we can gather some training data. So we have our robot chef process, and we have our input parameters, which are salt, pepper, mixing time, cooking time. We get some training data, so we ask users to give us some information about texture, flavor, and appearance. And by using this data, we can then use some optimization kind of techniques to optimize the kind of control processes to match a user's expectation of the omelette they receive. And we use one approach called Bayesian optimization. And Bayes' rule is something actually that's featured very recently in the rules, in the news, in response to the maths behind kind of some of the COVID kind of probabilistic methods. And it's a very common technique used in robots when we want to explore and identify a function that is unknown. Because we don't know how we map from control inputs to the output, so how people perceive the food. So what we use is a Bayesian optimization. And this is a black box estimation of our function, which is how we map our control inputs to our outputs. And we estimate the performance, so how we map these two from our inputs to outputs. We then sample, so we cook our omelette using our robot. We get our updated information from our omelette testers, and we update our model, and we repeat to improve our model over time and optimize for a given function, which in this case is kind of quality kind of the omelette. And in this way, we can improve the kind of quality of the cooked omelette. So we can improve the flavor, appearance, and texture. And what we showed is with relatively kind of through few cooking iterations, we could cook robots' omelettes in a fully automated manner that better met the requirements of those eating them. So a final problem I'm going to talk about is that of abdominal palpation. So this is performed by many doctors, and it's used for the identification of, for example, tumors or other abnormalities in the body. And as you can see, it's a really complex task. So the robot or the human here is using their hands to feel the body, the soft body, the hard inclusions, to allow them to make an accurate diagnosis. And what we're really interested in doing is how can we get a robot to perform some of these interactions and identify is there a tumor or not? So we've got a robot and it's fixed with this tactile sensor on the end of a probe. Now, obviously, we can't do this in real patients, so we have to start with what we call a phantom. So this is a mock-up of a human body. And we have, for example, livers, which have some inclusions in, and some areas of the liver which are considered healthy and kind of tumor-free. But this is a really nice example of the unsupervised learning. So here, we use the robot to search the abdominal phantom, looking for kind of areas where we have a tumor and we don't. And we can use unsupervised techniques to actually classify, does this area tested have an inclusion, is therefore kind of cancerous, or does it not? So here we can really take these very simplistic approaches but apply them to real world problems. Okay, so hopefully that's a quick introduction to what we're calling traditional robotics. Now, it's very effective in industrial settings. We've got high predictability, programmability. We have very top-down design, and we can create very complex intelligent systems with kind of some of these machine learning approaches. But what happens in the real world is a little bit different. And there's this really lovely quote, which really says it's comparatively easy to make computers exhibit adult-level performance on intelligence tests or playing checkers, but difficult and more impossible to give them the skills of a 1-year-old when it comes to perception and mobility. So how do we take this huge intelligence in terms of machine learning, deep learning, computer vision, and actually apply it to real-world scenarios? So this is a video taken from one of the DARPA challenges. This is a challenge run by the US government to try and develop increasingly capable robots. Now, the problem here is as soon as we take these incredibly intelligent robots and put them in complex environments, it's really challenging. So we put them in sand. We ask them to do things like walking through rubble, through sand. We ask them to try and open doors. And we have this disconnect here between these incredibly intelligent systems that are performing very poorly in the real world. And we can look at a number of different environments where we know robots in their current state are going to struggle. They struggle to perform the physical interactions and understand complex and structured environments. But these are things that as humans we're fantastic at doing. We can deal with these environments. We don't have to have seen a messy kitchen before to understand how to tidy it up. Or we don't have to have seen every single object before to know how to pick it up. So there's some kind of disconnect here between machine kind of intelligence as we know it, and this ability we have as humans to form really clever interactions with the environment. So how can we tie in some of this kind of intelligence we have as humans with kind of some of these machine learning techniques to create truly intelligent systems? Now, what we're really interested in is perhaps some of this actually lies in the body. Perhaps is there other ways of having intelligence which are not purely kind of computational intelligence? So I'm going to show you now a video of a fish swimming. So this is a video from the University of Harvard, and it's lovely, and it's showing we've got a flow stream and we have a fish swimming in the flow. And it's really interesting because actually this fish can swim upstream to this obstacle, and it touches it and it falls back and starts swimming again. And this to me seems like very clever behavior. It's performing some kind of interaction, some kind of control to perform the swimming. But interestingly, this fish is actually dead. So all the computation, all the decision making, all the control is simply a function of the body of the animal and the interaction of the water. And this is incredibly complex. If we had to sit down today and program or develop this robot to do this, it would be incredibly complex. Yet here, all we have is the physical structure performing this intelligent activity. So there's obviously something here in that intelligence is not just about machine learning, the brain, but there's something here that the body is performing some kind of computation. And another example here is what's called the passive dynamic water.
Institute of Technology had developed a passive walking robot.
So this is a walking robot that has no brain. So all it's using is its physical structure to allow it to walk. And again, walking, as we've seen in the video a minute ago, is really complex for robots. So here, once again, we show how we can use this physical intelligence in the body to allow really complex walking behaviors. So in the future, we've got to look at this kind of bio-inspired of what we're calling embodied intelligence. So where the body provides some physical intelligence to the robotic system. And here, one key thing is that the morphology, the structure, for example, in the fish, its fins, its structure of its bones are really important to actually performing control. And they enable some kind of self-stabilizing passive dynamics. And here we can actually outsource some of the control or the physical intelligence to the physical structure. So what we're trying to say here is intelligence is not just a function of the brain, but also the body and how it interacts with the environment. So going back to our think, act, sense, we actually have a slightly more complex setup because we have the physical structure of the morphology of the robot itself, and it can actually do some of the actuation and the sensing itself without actually having any physical control. And in this way, we can create more complex, more intelligent systems because we've actually outsourced some of this computation decision-making to the robot and its physical structure. So I'm going to give, to just quickly wrap up this presentation, a number of examples of this embodied intelligence. Now, the first one is soft robotics. And this is an area that we're really interested in at the moment. It's really growing in robotics, because if we look at the world around us, humans, animals, we're not rigid like we see robots, we're soft, we're deformable. And this gives us a number of advantages. It gives us a trade-off. We have the ability to have some kind of flexibility and adaptability to the environment. So if we have a soft hand picking up an object, it actually gives us some ability to have some error and some positioning, and it gives us this trade-off. Now, the downside of that is we lose some kind of force exertion and some precision, but it allows us to perform far more complex and resilient interactions with the environment. So just to give you one example here, so this is some work before on developing a new kind of sensorized gripper. Now, this is a fully soft gripper. And what we do is we have this outer sleeve. So this is actually a balloon, and inside it we have an origami structure. And what we can do is if we apply a vacuum to our outer balloon structure, the origami closes and it grips on the structure. But because it's deformable, it can actually grip many different objects. So here you can see the gripper deforming around the object and then enclosing it. And in this way, we can use very simple control to pick up a wide variety of objects. We don't have to control or select individual fingers. We can just close a single object. The other thing is we can actually do quite dexterous manipulation. So for example, if we wanted to pick up a complex object, so here we're picking up crisps. So here we have a potato crisps, and we can actually use this gripper to both perform very delicate objects here of grasping an individual crisp, but also perform, as we saw at the beginning, very high force kind of grasping of bottles of water. So it provides this adaptiveness and kind of to the environment that would be very hard to achieve with more rigid solutions. So another thing that we can use is materials. So I've got two examples here. So this is a robot performing some assembly of a drill system, but I just want you to watch what's happening with the Allen key. So you might have seen that the Allen key, we'll just watch that again, went into the gel there and then went into the head of a screw. And we've got some kind of adhesion or tack between those. So we're actually creating a vacuum seal. And that allowed us to pick and place objects with ease. So here we can actually use material properties to help with the gripping. So this is a very kind of clever kind of robotic system for doing this assembly, but we're really using materials to help and aid make this task easier. We've got a second task example here, which is the task of kitting, which is we want to select single washers or bolts to put in a tray, which then perhaps somebody might use to assemble our belt drive system. And what you might notice here is we're actually using adhesion. So we've got on the end, you'll see it again in a second. Yeah, here we go. We've got some adhesive on the bottom of that. So we're actually using the tackiness property of it to be able to pick up a single nut and then place it in a box. Now, again, if we had to control a whole robot hand to do that, that's incredibly complex, but we can use some of these material properties to aid. And another really exciting direction of research is actually we can actually get more human-like properties. And this is some work by a group in Brussels creating self-healing materials. So we can actually, like the skin, we can cut it and it heals back together. So we can start introducing some of these techniques. So if you break your robot, it heals itself. So here we can see there's physical damage. The robot can detect it's been damaged, but the material heals back straight away and it can work again. So we can provide these different sorts of intelligence that we see in humans physically and purely through material properties. So, final example is evolution and design. So, biology is incredibly clever. First of all, we can look at this idea of cell differentiation. So to build and construct animals, it all starts from these incredible things called stem cells, which then differentiate into all the different kind of cells that build up our bodies. Now, If we consider robots, at the moment, robots are built by people in a lab or a factory, adding together all these very complex systems, which are each very bespoke. And it's not a scalable way, yet we see biology offers this way to do kind of build up and differentiation. And also, how have we designed robots? How does biology design the structure of animals? We've had evolution, and if through many hundreds of years, we've seen the adaptation and the optimization of humans and other animals for the specific environment. Now, how do we do something similar for robots? So one example is this concept of mother robot. So this is a robot that builds robots. So this robot takes cubes and it actually combines cubes together to create new robots. So it's creating its children by adding these mini robots together. So it actually is using glue to achieve this. And in this way, it can then test its robots. So it designs, generates, and fabricates these robots from cubes. And then it actually tests them. So it actually is testing how far they can walk. So here it puts it together and they perform some kind of locomotion. So this mother robot creates these robots and then tests them. The idea being that over time, the robot can learn by combining different structures to develop kind of its own best robot. So it's kind of showing the evolution of robots through physical experimentation. Now, this is actually kind of really groundbreaking work and really exciting, but there is a problem here that the physical experimentation is slow. So if we've got to take 30 minutes to build and test each robot, we've got a real limit on the throughput there of how many robots we can test. So one thing we can do is start actually to use simulation tools. And we've created up a new, with some work I've been doing at MIT, we created new ways of actually searching and designing robots. And we do this in simulation by combining what we call a grammar. So in any language, we have grammars, and we can do the same for robots in the same way. Grammars describe how we can take words and put them together to make logical structures. So for robots, we can do the same. We have parts instead of words, which could be bodies, tails, joints, and heads. And we define rules, which allow us to define how we can combine these together. And with these different rules, we can perform what we call a tree search. So we apply one rule, and this could be add body to head. Then it could be add tail to head. And we can create all these trees, which allow us to describe how we can build these different robots. We can then actually test how these robots perform in simulation and optimize and select which robots perform best. So here you can see how we take our rules from our grammar, we create a kind of representation of these in the graph, and then we can convert it to a simulated robot. And what we do is we use various techniques to optimize the control and measure the performance. But by doing this, we can create whole families of robots with very different structures, and we can optimize them for different tasks. So here we have some robots optimized for running on flat terrain. So you can see they've got long front and low back legs. We can get some robots optimized for gap terrain. So example here, using their tails to help them propel them over the gaps. For stairs, we get these like frog-like robots bounding up the hill. And then finally, for rigid terrain, we get these kind of grasshopper-like robots. So here, it's not evolution, but we can do some kind of design search, which allows us to find the optimal body or morphology for a given task. And finally, I'm just going to end very quickly with our last example, which is using bio-inspired kind of humanoid systems. And one thing in the Bioinspired Robotics Lab at Cambridge we've been really looking to is this idea of the human hand and how the structure and the passive properties of it are really important. So we've developed new ways of fabricating hands which have rigid bones and soft ligaments. And we can then actually look at how can we, just by actuating the wrist, perform very complex tasks, in this case, piano playing. So we're trying to show that the physical structure is very important, and how can we use very simple control, but really make use of the physical structure to create intelligent, to perform intelligent tasks. And here is another example of a very human-inspired hand. So here the hand itself has no physical actuation. All we're doing is actuating the wrist, but we're using the physical intelligence of the hand and how it interacts with the robot to perform complex tasks. So here on the left, you actually see someone teaching the robot how to pick up the kind of objects with this hand. And then from that, we can perform some kind of learning of how to do this with different objects. But here we're utilizing the structure of the hand to be able to perform very complex tasks with only very simple actuation. So just to sum up, we've started off by talking about kind of machine learning, kind of hardcore intelligence, but we've also very much got this embodied intelligence. The morphology is important, and we can outsource some of the intelligence to the physical structure. So the key takeaway is really from today is that intelligence is a function of both the body and the brain. And in the future, we need machine learning, we need deep learning, but we need to really consider how we can bring it together with an intelligent body to make truly intelligent robots. And we want to close this gap between animals and robots. And interestingly, this just isn't about being kind of more clever. It's about what makes us, what makes us conscious and intelligent. And there's lots of really interesting ideas out there. There's some that hypothesize the fact that we can dream and we have consciousness is really important because it allows us to absorb and assimilate information. And really kind of, for our brains, it's incredibly important. We need this physical complexity in our physical structure, even going down to our muscles and our reflexes are incredibly computationally intelligent. And we also need things like curiosity and exploration. And we see that in animals, we see that in humans, and there's these concepts which we need to start to bring into robots to close the gap between animals and robots. Now, the future of robots, it's interdisciplinary, it's distributed, and it uses this concept of embodied intelligence. So the kind of key takeaway really is robotics isn't just all about computer science and sitting at a screen and writing code. It's really important having these tools for the machine learning based activities, but we also need to bring in lots of other approaches. We need material science, we need biology and chemistry, we need philosophy and mechanical engineering, all to come together in this very interdisciplinary and distributed approach to create truly intelligent physical systems. So thank you very much for listening to this rather long kind of introduction to both the kind of basis of machine learning and also perhaps the future, some of the new approaches that we're considering.